Welcome to the second part of this ionic polymerization. Now, if you recall that previously we discussed about the classification scheme of various ionic species. We had a discussion about the effect of solvent in the ionic polymerization process. We discussed about the ionophores and ionogens. Apart from this, we discussed about the ionic pairs and covalent species in the previous lecture. Thereafter, we discussed about the concept of equilibria between free ions and ionic pairs under the head of conductance studies. Then we had a discussion about the heat and entropy of dissociation of those ionic pairs being developed. Now, in this particular lecture, we will discuss about the various types of ions. Then we will discuss about the initiation and propagation steps with respect to the mathematical approach under the edges of ionic polymerization. And at last we will discuss about the effect of solvating agents. So, let us start with the triple ions. Now, at sufficiently high salt concentration, there is an increase of equivalent conductance. Now, if you recall that during the process of heat and entropy dissociation, we discussed the conductance concept. Now, these findings they were interpreted as evidence of association of ions with ionic pairs and sometimes leading to the formation of charged triple bonds and those who are capable of conducting electric current. Now, these triple ions sometimes they approximate relations, they possess approximate relations, and these are valid at not too low salt concentration, and sometimes it becomes useful. So, the conductance that is referred as the K dissociation upon the concentration to the power half or limiting conductance plus the kT that multiplied by the K dissociation into C to the square and conductance dash. Now, where kT is equal to kT minus is equal to kT plus. Now, here you see these are the equilibrium constants for association of free ions with ionic pairs into the triple ion, and these are the limiting conductance of the free ions and the triple ions. So, sometimes they are referred as the limiting conductance of triple ions, and C is the total concentration of the salt. So, all these things are implies together. Now, that is kT is equal to kT minus plus equal to kT plus. So, for the equilibrium you need to fulfill this particular relationship. Now, this particular relationship is valid for the range of concentration of salts high enough to maintain the ratio that is the free ion over C, that is less than 1, but sometimes sufficiently low to keep the ratio, that is the triple ion over C is less than 1. So, under these conditions K dissociation upon C to the power half is equal to the free ions over C, and the kT K dissociation multiplied by C to the power half equal to the triple ion over C. So, this higher salt concentration, but still for triple ions over C is less than 1, and the conductance is proportional to the C to the power half. So, that is one of the limiting factor. Now, when we talk about the higher ionic aggregates, now in several systems the dipole-dipole interaction sometimes lead to the formation of dimers of ionic pair and still higher aggregates. So, sometimes it may create the agglomeration problem, and this may lead to the higher molecular weight and higher viscosity, and ultimately creates a problem to the processability of those polymer being generated. Now, these are the readily formed in the poor solvents, that is the diethyl ether and hydrocarbons. Now, in the extreme cases of formation of aggregate, this sometimes lead to the micelles, or sometimes they may create the formation of micelles. Now, the large aggregates sometimes they provide a favorable environment for free ions, and distort the free ion-ion pairs equilibrium. Now, on the whole, the aggregates they are not reactive and they do not contribute to initiation or propagation of ionic polymerization. However, these they participate in the polymerization since they dissociate into a more reactive species with which they remain in equilibrium, and they form therefore the dormant polymers. Now, let us have a look about the initiation and propagation in ionic polymerization, and we will do some mathematical approaches and discuss the mathematical approaches those who are attributed to these ionic polymerization. These propagation perpetuated by the positively charged end group or induced by a positive end of a reactive dipole. It is sometimes known as cationic or pseudo-cationic polymerization. So, similarly, an anionic or pseudo-anionic polymerization ensues when a negatively charged end group or negative end of dipole, this constitutes the active propagating center. So, as a whole, the initiator or its fragment remains associated in some fashion with the active end of an ionically growing macromolecule during the entire period of its growth. So, let us take the example, that is the counter ion accompanying the initiating anion mentioned in this particular paragraph become now the chaperone of a newly formed polymer. Therefore, the propagation constant and the mode of monomer addition and the other characteristics those who are featured in ionic polymerization are usually affected by the nature of initiator. And as we discussed earlier that the initiator, nature of initiator, the concentration of initiator, then the affinity of the initiator with other monomer, this is a very vital issue which need to be addressed during any kind of polymerization, whether it is a radical polymerization or ionic polymerization. So, in this concept or in this regard, the ionic propagation, this differs from radical propagation since the initiator does not affect the rate constant of propagation of later polymerization. So, let us have a look about the mathematical approach of this initiation propagation in ionic polymerization. The simplest mode of initiation of polymerization, this arises upon the addition of an initiator or its active fragment, and this is usually denoted by X to a monomer that is represented by M. So, when we talk about this, then X plus M, they may form this one. Now, such an addition this could be reversible and the rate is given by minus dx over dt, that is equal to kt x m, that is k m. Now, this where this Kp, this is the rate constant of monomer addition to X m star, that is the ionic one, and this Ki and this minus Ki, they are the forward and backward rate constants of X addition to the monomer. Now, if we take the things like K minus I is less than this Kp in this equation, this equation which we discussed previously, this yields the rate of initiation, and this is termed in the under the head of first order in x and m. So, on the other extreme, sometimes we may go for the extreme conditions. So, on the other extremes, for k I minus, if it is greater than this kpm, the minus dx over dt, this pertains to the rate of initiator consumption while at equilibrium with the monomer. So, by this way we can discuss, or we can have these two extreme conditions. Now, the consumption is then the first order, is the first order in x, but it is thus of second order in monomer. So, that is minus dx upon dt is equal to Kp Ke x m square. Now, here this Ke Ki upon Ki minus K minus I. So, the addition is always exothermic, and when its exothermicity exceeds the activation energy of monomer addition to M star, the polymerization speeds up on lowering the temperature, and its apparent activation energy is negative. So, by this way we can start this initiation and propagation aspect. Now, it is beneficial when the rate of initiation is faster than, or at least equal to, the rate of propagation. So, under such condition, the polymers of narrow molecule mass distribution could be formed, and provided the system is living, that is the termination and chain transfer are virtually avoided or absent. So, in that case one may have one may write like this: the initiation and propagation of polymers by free ions. So, ionic polymerization, this may be induced by sufficiently reactive free ions. So, the prerequisite is that we must have sufficiently reactive free ions. So, this exemplified by this scheme, like we are having x plus C double bond C, x minus x C C C plus, or x minus plus C double bond C, this is x C, C minus. Now slightly modified schemes describe the initiation of ring opening, polymerization of heterocyclic monomers by free ions. Now they can proceed either by the route. I mean, there are multiple routes available. So x plus say CH2y, that sometimes CH2y plus, and sometimes this one. So these are the couple of examples which we can give, or sometimes like this, x plus y, this is bonded with this one, and this may form this particular group, and then x plus y CH2 x y minus CH2. Now these initiation resemble the respective propagation and usually induced by the free ions of growing polymers. So sometimes like this they can be represented as plus CH2, the CHY, CH2 CXY, CH2C plus XY, and CH2C, CH2 double bond CXY is CXY. So when we talk about the ring opening polymerization, they may proceed according to the schemes sometimes referred as CH2Y plus CH2Y, CH2Y, Y plus, or sometimes or CH2 CH2 Y plus and CH2. Now this is the analogous schemes schemes for the anionic polymerization. Now sometimes for simplicity this can be, we can noted as, now just this is for the sake of simplicity, that Pn plus m, this Pn plus 1, or sometimes Pn minus plus m, this is Pn plus 1 minus. Now it should be stressed, however, the system involving free ion with the exclusion of ion pairs or other aggregates, they are hardly known polymerization, and the polymerization induced by ionizing radiation. This is an example of polymerization involving only free radicals, free ions. So by this way we can give a small description of initiation and propagation usually induced by salt. This is the another way. Now, this consideration are limited, therefore, that part of system that acts as a free ion. Now, since free ions are usually formed by the dissociation of ionic pairs, the value of dissociation constant of the latter is important in determining the fraction of free ion participating in the overall process. So, the dissociation of ion pair is usually favored by dilution, sometimes lower temperature and the increasing solvating power of the medium. Now, let us have a look about the initiation and propagation induced by the salts, that the degree of dissociation of the salt sometimes initiating anionic polymerization, they may vary widely depending on their nature and the nature of the solvent. So, the solvation of free ion increases the degree of dissociation of their ion pair, but sometimes it reduces the reactivity of free ion because at least one molecule of the solvent has to be removed from their solvation shell to allow to contact with the monomers. Now, these free ions sometimes they are often most reactive initiating species, and they initiate the polymerization by direct attack on a monomer, electrophilic in cationic, nucleophilic in anionic processes. The intrinsic reactivity of an initiating or propagating ion, usually this depends on the charge density on that of its atom, which ultimately becomes sometimes linked with the covalent bond or with other bonds to the polymerized monomer. So, the rate of free ion addition to a series of monomer, this may vary with their nature. Now, in cationic polymerization, usually the rate increases with the increasing monomers nucleophilicity, that is the decrease in the order, like N vinyl carbazole is greater than vinyl ethers, is greater than para methoxystyrene, is greater than para methylstyrene, is greater than the cyclopentadiene, then it is greater than alpha methylstyrene, is greater than styrene and indene. So, this the reverse order governs the rate in anionic polymerization. Sometimes the substitution of alpha hydrogen of a monomer by a methyl group accelerates the cationic initiation or propagation, but it retards the anionic one. So, as a on the whole, the initiation is often efficient when the initiating ion is less stable than the one formed in the process. The position of attack by an ion is uniquely determined in the initiation of vinyl or vinylidene monomer, but unsymmetrical dienes to alternative sites of attack are possible. So, the preference being determined by the difference of electron densities. Sometimes we may look into the other concepts like the condition of electric neutrality depend upon the presence of counter ions in the polymerized solution in an amount equivalent to that of the initiating and propagating ions. The mutual attraction of oppositely charged ion, this sometimes lead then to association yielding a variety of species such as ion pair, triple ion, aggregates of ion pairs and so on. So, all coexisting in equilibrium with each other. Now, some of these associates, they act as initiator on their own, right, and contribute to the rate of initiation proportionally to their mole fraction Fi, sometimes referred as Fi, weighted by their characteristics initiation rate constant K I n I. Now, this the apparent initiation and propagation of initiation rate constant the Kin apparent is derived from the experimental data, and therefore, usually we may use this equation, that is the Kin apparent is equal to the summation of Fi Ki n and I. Now, a similar relation provides an apparent rate constant of propagation of ionic polymerization, since the propagating polymer sometimes may form a mixture of distinct species of I. Therefore, the experimental derived overall propagation rate constant Kap is usually given by Kpap, that is summation of Gi Kpi, where this Gi denotes the mole fraction of a respective kind of growing polymer I's, and Kpi is their propagation rate constant. Now, let us talk about the ionic system. Now, at least two kind of ion pair, they are participating in the reaction ensuing in many anionic system, and they are highly reactive, and they loses the ionic pairs and relatively unreactive tight contact pairs also. The reactivity of loose ion pairs, sometimes they depend on the nature of species solvating the cation, although the variation of solvating agent rarely affects their reactivity by the factor greater than 10. The most extensive data reveals the behavior of ion and ionic pair in an ionic system. It was obtained through studies of anionic polymerization of styrene in ethereal solvents or ethereal solvents. Now, in the absence of impurities, oxygen, moisture, etc., these reactions are proceed free of termination and chain transfer. That is, the pertinent polymers, they are termed as the living polymers. Now, let us talk about the dependency of propagation rate constant on cation size. Now, the propagation rate constant is affected by the nature of counter ions. So, approximately the lowest value is found in lithium ion pairs, that is the Kp is equal to 0.9 m inverse second per second, but higher for the potassium ion, Rb ion and Cs ion, the respective Kp values are in the range of 20, 1.5 and 24.5 meter inverse per second. Now, this is the schematic representation of a vinyl monomer addition to the ionic pair. Now, you see that here we are having the initial one with these two the charges, and then this is the transition state, or sometimes you may refer as the intermediate state, and this one is the final one. So, the increase in the cation size seems to be to enhance the reactivity of tight ion pair, and it is a plausible inference. The addition of a monomer to a tight ion pair, this has to proceed simultaneously with a transfer of cation from previously active center to the newly formed one. Now, this we have already represented in this particular figure. Now, such a transfer is usually opposed by the Coulombic attraction between the ion of the pair. Now, the attraction decreases with the bulkiness of cation, and it is a very common phenomena. So, while their complete solvation is hindered by the crowdiness in the transition state. So, if there are more and more particles being formed in the transition state, then it is usually hindered. So, the change in the electrostatic interaction sometimes might the cause of observed enhancement of propagation. So, for a sufficiently large but sometimes not referred as too large cations, the transfer may take place without separation of ions. Now, at last we discuss about the effect of solvating agent. So, although the suppression of concentration of loose ion pairs sometimes coexist in the equilibrium with the tight one is not feasible, the increase in their proportion is readily accomplished by the addition of solvating or coordinating agent to their solution. Thus, they may produce the loose pair separated by the added agent. a large enhancement of the rate of initiation or propagation is sometimes achieved under this phenomena. Now let us discuss about the push and pull type of mechanism. The cooperative action of anion and cation, so when jointly interacting with the monomer, this is another important factor that affects the rate of addition. Now sometimes this is known as a push and pull mechanism, like this one is pushing and thereby this is adding, but its accelerating effect this means the separation of those ions. Therefore, its contribution to the reaction is large, then the separation of ion retards the monomer addition. Apparently, the coordination of cryptate, that is a coordination complex in which a metal cation is bound within a three-dimensional interior cavity of a cryptant, this cryptate with the cation that may separate the ions of a pair reduces the beneficial effect of cation, and the resulting loss is greater than the gain arising from the reduced electrostatic work required for the partial ion separation. So, this is again a very important thing which we need to address. Now, we have gone through about the solvation ability, solvating agent. We discussed about the initiation propagation induced by varying agents in this particular chapter, and we took the help of this particular reference for conceptualizing this particular lecture. And if you wish to have further studies, then you may go through this particular reference. Thank you very much.